Thank you. Thank you very much for giving me this opportunity to join your wonderful webinar. It's my pleasure to share with you our work or my work. The title, as you see, is Ungraded when Absorbing Primary Ideals. This work is joint work with my friend, Professor Poincaré from Jordan University of Science and Technology. First of all, we will talk about the basics or the definition, what's a graded ring. Throughout this article, G will be a group and R a commutative with commutative ring with non-zero unity. R is said to be G graded if we can write R as a direct sum of components, R sub G. R sub G are additive subgroup, and they should satisfy this condition, Rg, if we multiply, and this multiplication is the usual multiplication of the ring. Rg by R sub H should be a subset from Rgh, and the operation between Gh is the operation on the group G. So the product between R sub G and R sub H is the product of the ring, and the operation between G and H is the operation of G. Should be maybe addition, maybe multiplication, maybe star, as you like. And this should be true for all GH in G. As we said before, the component R sub G should be an additive subgroup for all G in G. In fact, this comes from the direct sum. If we take any X in R, then X should be written uniquely, in fact, as a summation of xg, and xg are the component of x in Rg. We will call the set of all homogeneous elements of R is H of R, and R sub E, the component R sub E, where E is the identity of the group G, it will be subring, and it will contains the unity when R contains the unity. So this was proved in reference 5 that Re is always a subring of R and contains the unity. Now, what about the definition of a graded ideal? If we have a graded ring R and we have an ideal I is said to be a graded ideal if it can be written again as a direct sum of the component I intersection R sub G. Or in other words, equivalent characterization for the definition, if we take X in I, and of course X will be written as sum of components, all the components of X should be remains inside the ideal. This is the definition of a graded ideal. The first question, if we have a ring and we make it graded, can we have all the ideals inside this ring graded? The answer is no. So here the following two examples show that an ideal of a graded ring is not necessary to be graded. We have two basic examples. If you take the Gaussian integers, z of I, and you take g equals z2, it's the group of integers mod 2. If we have the following basic, in fact, graduation, you take R0 equal set of integers and R1 equals I of z. It is easy to see that every element in R is written as A plus IP. So A will be the first component, R0 equals z, and IP will be the second component, IZ. So this is a graded ring. If we look to the ideal generated by 1 plus I, this is an ideal of R, but in fact it is not graded, because if it's graded 1 plus I in I, so each component of this element should be in I. So in particular, 1 should be in I, and this is not true, because you know, if the ideal contains the unity, it will be the whole ring, and this is a contradiction. So this is an example, an ideal inside a graded ring, but it is not a graded ideal. Another example, we go to the ring of polynomials. We take K a field and the group Z of integers, and we take the ring of polynomials K of X. This is the ring of polynomials with coefficients from a field K. We make graduation over Z, so we take R sub n equals 0 when n negative, R0 equal the constant, and Rn equal Kx to the power n when n is positive. In fact, this is called the standard graduation or the usual graduation of the ring of polynomials. Again, if you look to the ideal generated by x plus 1, this is an ideal inside R, but it is not graded because the element x plus 1 inside I, if I is graded, all the components of this element should be inside I, but you know, x, it's a component, x lives in R1, should be in I, and this is not true. Again, 1 is a component living inside R0, so it should be inside I if I is graded, and this is not true. So these two examples show that not every ideal inside a graded ring is a graded ideal, and this is give importance for our work. In fact, if we have two graded ideals, then the sum and the product and the intersections of them will be graded ideal. This is proved in reference 4. And another result, if we take a homogeneous element, then every ideal generated by this element will be graded. And this is important one, in fact, too, because this is the easy way to construct a graded ideal. To construct a graded ideal, just you take a homogeneous element living in some component, and you take the ideal generated by this element, you will directly obtain a graded ideal. This is the definition of a graded radical. You know the radical in the ring, so we just redefine using the graduation. So this is the graded radical of I. If we have a proper graded ideal, then the graded radical of I is defined as follow, and it is similar to the definition of radical. In fact, this ideal is always a graded ideal, and this is, it has been proved in reference 8. So we can find every time graded ideal if we want. Our talk is about generalizations of a graded prime ideal. First of all, recall the definition of a prime ideal. A proper ideal B of R is said to be prime ideal if whenever xy belongs to R such that xy belongs to I, then either, sorry, this is a mistake, this is the ideal I here, xy in I, then either x belongs to I or y belongs to I. This is the definition of a prime ideal. Now, what is the definition of a graded prime ideal? Just we redefine the same definition, just we replace the elements you are taking from R. Now you are taking them from homogeneous of R. So again, if we have a graded ring R and we have a proper graded ideal, so the first condition should be graded ideal, then I set to be graded prime if whenever x, y, and h of R. So this is the difference. Here you take the elements from R when you're talking about prime ideal. When you are talking about a graded prime ideal, you take the elements from h of R, so they should be homogeneous. And the remaining of the definition is the same, such that xy belongs to I, then either x belongs to I or y belongs to I. Clearly, from the definition, if I is a prime ideal of R and R is a graded ideal, then of course I will be graded prime ideal. But the converse is not true, and this gives importance for this way. So it's worth it to study such ideals. Now I will give you an example about a graded prime ideal, which is not a prime ideal. So see the following example. Indeed, the following example shows that the converse is not true in general. So again, we take the Gaussian integers and make a graduation over Z2. We have R0 equal the integer Z and R1 equal IZ. We take the ideal that generated by 17. Because the 17 is a homogeneous element, because it belongs to R0, so this ideal is graded. Every ideal generated by homogeneous element will be graded by the previous lemma. So this I is a graded prime ideal. We show that this I is a graded prime ideal now. We take two elements from H of R such that the product belongs to I. We are going to show that either X belongs to Y or Y or to I or Y belongs to I. So when you take two elements from H of R, the components are just two components, R0 and R1. So we have, in fact, four cases. either both elements from R0 or both elements from R1 or one from R0 and one from R0. So we have three cases, in fact. Case one, we assume that the both elements are from R0. In this case, they are integers, such that 17 divides the product. And you know 17 is a prime, so 17 should divide one of them. 17 divides X or 17 divides Y, as 17 is prime number, and you are working inside the integers, which implies that X belongs to I or Y belongs to I, and we are done. The case two, I take the both elements from R1. So in this case, X equal IZ, IA, Y equal IP for some AP integers. Again, 17 divides XY, which is minus AP. When you product X, make the multiplication XY, you will have minus AP. So 17 divides AP, and again, 17 is a prime. 17 divides A or P, and then easy calculation, you will have 17 divides X or 17 divides Y, which means that X belongs to I or Y belongs to I. Case 3, we take X from R0 and Y from R1. We have Y equal IP for some integer P. Again, 17 will divide XY, which is IXB. And this means that IXB would be written as a 17 multiplied by an element from R for some, again, alpha, beta, and Z. Again, when you have to solve these equations, you will have XP equals 17 beta, and this means 17 divides XP, and you should remember that both of X and P are integers. So again, 17 divides X or 17 divides P, we will have our result. Of course, one can similarly show that X belongs to I or Y belongs to I in other cases. So in fact, we prove that I is a graded prime ideal. Indeed, on the other hand, I is not a prime ideal because I can choose two elements from R, which are not homogeneous, 4 minus I and 4 plus I. If you make the product, it will have 17, so it will belongs to I, but neither 4 minus I belongs to I, nor 4 plus I belongs to I. So this is an important example talking about graded prime ideal, which is not a prime ideal, and this is to make our work worthy to study this course. The graded prime ideals have valuable performance in the graded commutative rings. There are various procedures to generalize this concept. In fact, in HTTP Journal of Mathematics in 2019, we gave a generalization of a graded prime ideals called the graded to absorbing. The definition is a propagated ideal P of R is to be graded to absorbing whenever APC belongs to H of R such that the product inside P, then either AP belongs to P or AC or PC. So you absorb two elements. On the other hand, in Turkish,
you have 2 minutes.
Oh,
Please summarize.
So my concept is a propagated ideal is to be graded one absorbing primary if whenever three elements in H of R such that the product in P, then X, Y in P or Z in the radical. This is an example talking about graded one absorbing primary, that it is not a graded primary. So this is an important example that we are talking about a new class, in fact. And we proved that, you should, I will back here. We proved in this implication, in fact, graded primary gives our concept, and our concept gives graded to absorbing primary ideas. And we proved the converse of each implication is not true. This is another example about the converse. So our results, we prove that if P is a graded one absorbing primary, then the radical is a graded prime. This is important one. This is another proposition, but I want to talk about this one, in fact. If we have a graded one absorbing primary ideal, then the residue ideal, this is always a graded primary for every non-unit element belongs to H of R, but it is outside B. This is very important too. We proved that if we have a graded one absorbing primary ideal, then for every non-unit, you have either P is a proper subset of residue ideal or the radical equal the radical of B. we prove some characterizations the following. B is a graded one absorbing primary ideal if and only if B is a graded primary. We prove that B is a graded one absorbing primary if and only if B is a graded primary ideal of R. So this is important characterization. And this one. Finally, we prove that the intersection will be graded one absorbing primary under the condition they have the same radical. They should have the same radical. And we have examples that in this necessary condition. We study this concept about ring homomorphism and ring epimorphism, in fact. And we make another characterization, this one about this concept. In fact, I should mention that we follow this reference in our work. This reference, it's from Journal of Algebra and its application 2020. It is for Ayman Badawi and Jellikel. And our results somehow motivated by this reference from Badawi and Jellikel. Thank you for your attention.
Thank you, Professor Davas.